In this video, I want to go through the process of finding the eigenvalues and eigenvectors of a matrix. And by finding the eigenvectors, what I really mean is finding a basis for the eigenspace that goes with each eigenvalue. So here we have a matrix. I want to find its eigenvalues and eigenvectors. And the first step is going to be to find the characteristic polynomial of the matrix A. This polynomial has been mentioned. It was mentioned in the 3 blue, 1 brown video, but I want to remind you what it is because I don't think he refers to it as the characteristic polynomial. He just says what it is. So the characteristic polynomial of a matrix is the determinant of the matrix A minus lambda I. And this is a polynomial in the variable lambda. So A minus lambda I is the matrix we want the determinant of, and that will give us our characteristic polynomial. So A minus lambda I is really just saying subtract lambda from each diagonal entry of A. So we want to find the determinant of this. I'm going to subtract lambda from each diagonal entry of my matrix. And this determinant will give us a polynomial in lambda because we know that by cofactor expansion or by one of those formulas, you do get a polynomial in the entries. So generally speaking, the right approach to finding the determinant of this matrix, a matrix with variables in it, is cofactor expansion. Now here, it's relatively obvious that we should do cofactor expansion because of this row that contains 2 zeros. But even if we weren't so lucky, we would want to do this with cofactor expansion because if we do row operations, we start dividing by polynomials and variables, and that can get messy. You can do it, but I generally recommend just do cofactor expansion. All right, so this determinant is not too bad. We cofactor expand along row 2, and what we end up getting is that only the second term is non-zero. So this is the 2 entry, so -1 to the 2 plus 2 times 2 minus lambda, our entry, times the determinant of what's left when we cross this out. So minus lambda, minus 1, minus 2, 1 minus lambda. So that whole -1 term disappears. We just get a 1. And then we can calculate this determinant using the formula. And if we distribute this out, we get this. And there's this principle that I have in mathematics that unfortunately is not always emphasized by everyone who teaches math, which is that there's no such thing as simplifying an expression. An expression is only simple if it's simple for the application that you want. And so I've started to try to find this characteristic polynomial, and I should have some sense of where I'm going. So where am I going? I'm going to factor the characteristic polynomial to find the eigenvalues. With that in mind, I would be crazy to distribute this out because I've already partially factored this characteristic polynomial, right? I could multiply this out to make it look more like a traditional polynomial. That would be a waste of my time. It would make things worse. So I actually want to factor this thing because that's my goal. And I'm going to rearrange this because I struggle to factor things if they're not in the right order. And I see that I can factor this as lambda minus 2 times lambda plus 1. Now, I'm going to write this in a slightly different way. I'm going to take a -1 out of the first term and make it a lambda minus 2 because I'm more comfortable with that. And so I'll write it like this. All right, so I've calculated the characteristic polynomial and I've factored it out. I should point out Nothing wrong with calling this x instead of lambda, right? If you're more comfortable working with variables that just have traditional letter names, just do that, right? Don't force yourself to work with lambda as your symbol. It's not important, right? It doesn't matter what we call our variable as long as it's not something we've used previously in the problem. All right, so we found our characteristic polynomial in the sense that we got to the point where we had it in a factored form, and this gives us our eigenvalues. Our eigenvalues are the roots of the characteristic polynomial, the values that make it 0. And so my eigenvalues are lambda equals 2 and lambda equals -1. And notice 2 is a double root, which will matter, kind of. We'll see later how that matters. These are my eigenvalues. All right, I found the eigenvalues of this matrix. How do I find the eigenvectors? Well, let's go back to our overview. I need to solve the linear system a minus lambda I v equals 0 to find a basis for the eigenspace corresponding to lambda. How does this look? Well, let's do lambda equals 2. So what I'm doing is I'm taking this matrix, we'll write it as a matrix rather than a determinant, and I'm going to replace lambda with 2. And I'm going to solve the linear system where this equals 0. And if you're wondering, why do I do all of this? There will be a why this works section at the end of the video for those who want kind of a deeper dive into, what we're actually doing here. Okay, so I need to solve this linear system. First, I should simplify things. And I get to here. I want to solve this linear system. I need to reduce it to reduced row echelon form. And so I could do this in a bunch of ways, but I'm actually working this out because it's normally I would kind of skip through this, but it's so straightforward for this matrix. I'll do -1/2 row 1 in place of row 1. And then I can just cancel out row 3. That is if I add 2 row 1 to row 3 and replace row 3 with that, I get my reduced row echelon form. And when I solve this, I end up getting that the solutions to this are all matrices of the form this. Here I made S the parameter corresponding to the free variable given by the third column, and T the parameter corresponding to the variable given by the second column. All right, so I've found a basis for my eigenspace. V lambda is the span, or I said V lambda, but we know what lambda is. I'll call this V sub 2. Right? The eigenspace corresponding to 2 is the span of these two vectors. So any linear combination of these vectors will have 2 as an eigenvalue. It will be an eigenvector, and nothing else will have 2 as an eigenvalue. So quickly back through the process. I have my matrix. I subtract away lambda from all the diagonal entries. find the determinant, probably using cofactor expansion, and factor it. Keeping in mind that if I get lucky and I already end up with a factored expression, there's no reason to multiply that out. Think where you're going. I find the roots of the characteristic polynomial. These are my eigenvalues. And then to find an eigenspace corresponding to one of the eigenvalues, I plug in that value for lambda and solve the system of that matrix times a vector equals 0. Solve that system. The solution to that system, it's a homogeneous system. The solution set is a vector space, a subspace of Rn. And once I have a basis, that's a basis for the eigenspace. And I'll point out we could do the same thing for lambda equals 1, but I'll leave this as an exercise to the viewer if you want. And I'll just tell you what you'll get as an answer. And I should point out that anytime you solve one of these things, you could get a different basis depending on the kind of how you set things up. There are lots of different bases for the same space, but they'll be the same space, right? So you'll get something along the lines of this. Did I say lambda equals 1? I meant lambda equals -1. The eigenspace corresponding to -1 is going to be one-dimensional, and it's going to be spanned by this vector. And so you may have gotten a multiple of this vector, right? It's a one-dimensional space. Then you did it correctly. That's fine as well. Okay, so I want to go and look at this picture. And let me make sure that I have this set up exactly how I want. What I want to do now is just really quickly look at what this looks like, just the linear transformation. So this is the standard basis. And if I apply my linear transformation to three-dimensional space, this is what the linear transformation is doing, something like that. And let's look at it instead in terms of eigenvalues and eigenvectors. I'll leave the standard basis up for a second. So these are the two eigenvectors that we just found corresponding to lambda equals 2. And this is the eigenvector corresponding to lambda equals -1. Clicked on the wrong screen. That's not what I wanted to move around. Yeah, so we can kind of see this. And now if we animate this linear transformation, what we'll see is the purple vectors just doubling in length and the orange vector getting reflected, right? -1 its length. And finally, let's get rid of this standard basis because it's cluttering up the screen, and let's add in pictures of the eigenspaces. So the one that we found, the lambda equals 2 eigenspace, is this gray plane. And this orange line is the lambda equals -1 eigenspace. And one final time running the linear transformation, you can see that everything in the gray plane stays in the gray plane and gets multiplied by length 2, by size 2. It stays in the same spot, it doubles its length. And everything in the orange line is just reflected to negative itself. All right, so before getting into why this all works, I think it's nice to have some sense of what you should expect. And so let me explain what I mean by that. It's always nice to know, to have some sort of way of looking at an answer and saying, oh, that's not right, or oh, that's reasonable. So what can we expect? So a few things. Each real root of the characteristic polynomial is an eigenvalue. And there are no other real eigenvalues. So that is when you factor the characteristic polynomial, there's no way that you can end up with something that doesn't have eigenvectors. Those will exactly be the eigenvalues, the real eigenvalues of the matrix. I keep saying real because when we start talking about eigenvalues and eigenvectors, the complex numbers are kind of lurking in the background. They do matter. We noticed that we got one eigenspace with dimension 2 and one eigenspace with dimension 1. And you may have realized that our characteristic polynomial had some suspicious kind of things here, right? We had 2 lambda equals 2 roots and 1 lambda equals minus 1 root. And that's not totally a coincidence. That's not always going to happen. So the dimension of each eigenspace well, for one, it's at least 1, right? For something to be an eigenvalue, it has to have some non-zero vector that it sends to a multiple of itself. So it's at least 1, and it's at most the degree of lambda as a root of the characteristic polynomial. So in our example, 2 was a double root. And so going into the problem, solving it, I knew that, well, the dimension of the eigenspace was either going to be 1 or 2. It couldn't be bigger than 2 because that was the degree of the root. And for the lambda equals minus 1 eigenspace, I knew going in, look, this is a single root, and so it will have dimension 1. And then that's what we can expect. And just a quick warning, we're working over the real numbers. And so the characteristic polynomial might not fully factor into linear terms. So for example, if this is our matrix, B equals, let me make sure I detail, I'm not. Yeah, oh, sorry, I wanted to make sure that I wrote down the matrix that I put into the example. If I look at this matrix, every polynomial factors over the complex number. We haven't talked a ton about complex numbers in this class, but this is a really easy matrix to find the characteristic polynomial of. You can do it as an exercise. It ends up being this. This is the characteristic polynomial, and this term doesn't factor. Its roots are plus and minus I if we're working over the complex numbers. And so when that happens, these do not correspond to real eigenvalues. The only real eigenvalue in this case is 3. And let's look at that picture, because I do think it's worth showing. The 3 blue 1 brown video showed this sort of situation, and let's quickly run an animation. You can see that the x standard basis vector, 1, 0, 0, is tripling in length. And the other 2 standard basis vectors, so in the yz plane, you can see that the yz plane is getting rotated. So we're expanding in one dimension and we're rotating around the other 2 dimensions. And you can convince yourself, if you think about it, that in that situation, the only eigenvectors are vectors lying on the x-axis. So we might have a characteristic polynomial that doesn't factor over R. That's not a problem. It doesn't affect our process, but we might end up with terms that don't factor over the reals. Okay, the final thing I want to talk about is why this works. And I think it's not too bad to understand why it works, although I wouldn't say it's easy. We want to know whether this equation has solutions. And when you rearrange this equation, AV equals lambda V. I don't know why I decided to write this here. I think it's because the determinant's right here. When you rearrange it, that's the same as saying that A minus lambda I times V equals 0. And so we know that we'll have a solution, right? We'll have a solution when V is 0, but V is 0 is not an eigenvector. So we want to know when it has non-zero solutions. In other words, when this is A minus lambda I is not an invertible linear transformation, and that happens exactly when the determinant of A minus lambda I is 0. So we want to know when this determinant is 0, which is why we set this up, find the characteristic polynomial, and find its roots, because that's what makes this 0. So that's why these are exactly the real eigenvalues, because the definition of an eigenvalue is that this equation has a non-trivial solution. And we rearrange that and realize, oh, we can answer that sort of question with determinants. And then once we have the eigenvalues, all we're trying to do is figure out, well, what are the non-zero solutions to this, which is exactly what we did here when we set this up. We plugged in lambda equals 2 to this matrix, set it equal to 0, and solved for lambda. And so that's why it works. It's not obvious, it's not simple, but it really is just a quick we're quickly taking the definition of an eigenvalue and an eigenvector, rearranging it a little bit, applying our knowledge of linear transformations and how the invertible linear transformations relate to the determinant, and exploiting that to be able to do these calculations.